Lesson 2.6, Graphs of Rational Functions. Again, this is your homework assignment to watch this. I do not have notes online for you, so you will need to take your own notes. I will post notes online after Monday, but I'd really prefer you to take notes on this, including the sample problem that we'll be working later. So your homework assignment is to take notes and make sure you have that so I can see that on Monday. 2.6, Graphs of Rational Functions. I have an opening cartoon for you. I'll let you read it. And you are welcome to offend me anytime you want and tell me Ms. Othmar never did it the way I'm teaching you, but that's fine with me. What's this lesson? We're going to be talking about something called rational functions, and I'll define them for you in just a second. I'm going to show you how it's related to a function we looked at briefly at the beginning of the year called the reciprocal function. We're going to be talking about limits and asymptotes, as well as y and x intercepts for these types of functions, and you'll see how it ties in with what we've already been studying. Limits I'm really going to wait and talk about on Monday because I think that's probably the most confusing part of the section. So I'm going to save that for Monday, but I will talk about asymptotes, and we will look at some graphs and continue on. And why are these important? They are used in calculus, so you will need to know these and understand their behavior so that you can do better in calculus. And they do come up in scientific applications, particularly those that use inverse proportions. What is a rational function? It's basically a polynomial function it's actually two polynomial functions. This time we have f of x like before, but we also have a second polynomial function, g of x, and one f of x is divided by g of x. So it's called a rational function. So remember, f of x can be anything as simple as f of x equals 2, or it could be more involved. It could be f of x equals x squared plus 5x plus 6. And then g of x could be another rational function or polynomial. It could be like x plus 1, or maybe g of x is more involved. Maybe g of x is also x cubed plus 5x plus 6. We take these two functions and we divide them by each other, and we end up with something called a rational function. Notice it's not a polynomial function by itself, because with a polynomial function you have to have all of your terms in the numerator, if you will. In other words, the exponents need to be positive or whole numbers. So let's look at an example and see how we can study it. I put on the board r of x is 2 divided by x plus 2, and we're going to analyze it. But I'd like to compare it, first of all, to the reciprocal function over here to the right. So if you look at this function over here to the right first, that's the reciprocal function, 1 over x. And that's what it looks like, and I think if we build a chart, you can see why it looks the way it does. When x is a very small number, close to 0, say 0.01, when you divide by 0.01, you end up with 100. So you can see as x gets very small, the y values get very large. As a matter of fact, the limit as it approaches 0 from the positive side is infinity. So you end up with a limit up here of infinity. On the other hand, if x gets large, if you put a large number for x like 1,000, f of x is 1 divided by 1,000, or 0.001, and you can see that the limit as x goes very large out here, your y values, f of x, will approach 0. Again, I'm going to talk more about limits on Monday, but that's the basic idea of these reciprocal functions. On the other hand, if x is a negative number, you get the same graph rotated 180 degrees about the origin. If you plug in values of x that are negative, like negative 1,000, you'll see that your answer is negative 0.001, but again approaches 0 from this side. But when x is approaching 0 from the negative side, the y values go to negative infinity. So that's the reciprocal function. How does this function, r of x equals 2 over x plus 2, vary? You'll see it looks very similar. The 2 in the numerator doesn't do much. It makes the graph maybe a little bit steeper, stretching it out the same way 2x squared is a little bit more stretched out than x squared, but basically 2x squared looks like x squared, and 2 over x looks about the same as 1 over x, just stretched out. The x plus 2, though, shifts it left 2 places. You can see that we have a domain problem when x is equal to -2. When x is equal to -2, we end up having a divide by 0 situation. Can't do that. That creates what I call a vertical asymptote. So just like in the original problem, when x equals 0, we have a divide by 0 situation, and we end up with a vertical asymptote at x equals 0. When I shift the graph to r of x equals 2 divided by x plus 2, we have a domain issue at x cannot equal -2. And that's what they're going to tell you on the next screen. Again, the limits, which we'll talk about on Monday, still approach infinity and negative infinity as it comes in close to -2 from the positive side and the negative side. All right, I'm going to cover this slide Monday, so do not worry about it for your notes. This slide, worry about for your notes. How do we find these things called vertical asymptotes? And for that matter, how do we find the x-intercepts and y-intercepts? With vertical asymptotes, they occur anytime you end up with a divide by 0 situation. In other words, anytime this polynomial you have in the denominator equals 0, whenever g of x equals 0, could occur never, it could occur once, it could occur 100 times. It just depends on the degree of your polynomial in the denominator. You have the potential for a vertical asymptote. The only time you won't have a vertical asymptote is if the same value of x that creates a 0 in the denominator also creates 1 in the numerator. That's a case we'll cover on Monday. But for right now, all of your problems, if you end up with g of x equal to 0 in the denominator, you're going to have a vertical asymptote. X-intercepts, in other words, the zeros, are the same as what we've talked about before, except now you need to look at the numerator. If f of x in the numerator is equal to 0, we find all those zeros, you're going to have an x-intercept. Again, assuming that it's a real value. And in this section, we're only dealing with real. We're not going to deal with complex solutions that are not real. So that will create an x-intercept. The final term we're going to calculate is the y-intercept, and that occurs, as always, when x is equal to 0. Whatever y value we receive is going to be the y-intercept. With all three of these, that assumes that when the numerator is 0, the denominator is not 0 at the same time. Monday, we'll talk about it. But for right now, we're going to look at numerators, denominators when they're equal to 0, and then we're going to look at what value we get when we plug in a 0. So let's take a look at a sample problem, one that I'd like to have in your notes. And let me erase what I've got up here and start from scratch. Looks like I have to erase by hand, because this is the second time I'm preparing this audio, and I'd like to walk you through this step by step. Even though the problem just looks for asymptotes, we're going to find out where are the asymptotes. We're also going to find out where are the x-intercepts, because I'm interested in that. And I also want to find out for this problem, where is the y-intercept. We'll take them in the order that they've asked. First with the asymptotes. With the asymptotes, we're going to look at the denominator function and ask ourselves, when is this equal to 0? And they've already factored it for us, so they've done our work for us. We just need to now interpret these linear factors, and the first one means when x equals -1, and the second one equals x equals -5. So if I put a graph up here, the key points are going to be at -1 and way out there at -5. There's 2, 3, 4. We're going to have a vertical asymptote. Notice in both cases at -1 and -5, the numerator is not 0, so they are indeed vertical asymptotes. Now to find the x-intercepts, we're going to look at when does the numerator equal 0. Again, they factored it for us, so that's easy to see. At x equals -3 and x equals +3, we're going to cross the x-axis. So I'm going to put a little point right there at -3. And I'm going to put another one out here at +3 because I know that's where it's going to cross the x-axis. The final point I want to draw to your attention is where is the y-intercept? And to get that, excuse the bell in the background, I'm going to keep talking assuming it's not bothering you. We're going to plug in a 0 for x and see what value we get. So when I plug in a 0 for x, the numerator becomes 2 times 0 plus 3 is 3, 0 minus 3 is negative 3. In the denominator, I get 0 plus 1, which is 1, times 0 plus 5, which is 5. 2 times 3 times negative 3 is negative 18 over 5. That's about negative 3.6. So my y-intercept is going to be somewhere down here between 3 and 4, somewhere right there. At this point, I haven't really given you enough information to graph it because we haven't talked about the limits and how these asymptotes work, but I will tell you that the graph will look something like this. It's going to come in here from about 2 and nosedive down. Then it's going to pick up from up here and it's going to nosedive down, going through our x-intercept point. And then on the other side, and I might have that one. Nope, apologize. I've got that wrong. Oh, great. I may have just lost all of my writing. If that's the case, yeah, I'll go to the next screen. And at this point, yeah, I'll just graph it for you on this screen. Again, at -1 and -5, we have our asymptotes. Over here, we've got our x-intercepts at -3 and 3, and we know it crosses down here, right there. So what does the graph look like? It's going to come in like this, about 2, and I forgot it's not crossing the x-axis, so it's going to shoot up. Then this one's going to come in from down there and go up there and approach the asymptote. And then over here, it's going to come in, cross our y-axis, and bend over like that. Do not worry about the graphing for tonight or your notes. Just make sure you know that the asymptotes are at x equals -1 and -5. The zeros are at x equals -3 and 3. And the y-intercept's about 18/5. Let's do another problem so that you can see this. Find the asymptotes and intercepts of this problem. Asymptotes, look at the denominator. The asymptotes occur at x equals 2 and x equals -3 because those are the two values that cause your function to go to 0. So one asymptote is going to be right here at x equals 2. The other asymptote is going to be over here at -3. Look at the numerator to say where does it cross the x-axis. It's going to occur at x equals 1. It's definitely crossing the x-axis right there. And then finally, if you want to know what is the y-intercept at f of 0, we get -1 in the numerator, plug in a 0 in the denominator, and you have -2 times 3. That gives you positive 1/6, somewhere just barely above here. It is going to cross over. And we'll talk about the graphs and so forth of how you get what the asymptotes actually look like. On this particular problem, if you put in a really big negative number, it looks like you get -3, -4. You get a positive number. I think it's going to look like this. It is going to come in like this and finish up like that. So we'll take a look at that on Monday. One final problem I want to leave you with since it's Halloween is I want to tell you about a mathematician that spent some time studying rational equations. Her name was Maria Agnesi. She was an Italian. She was the oldest of 21 children. Yes, you heard me right, 21 little youngsters that she was the older sister for. She was a genius. She was born in Italy back in the early 1700s, I think around 1711. And by the age of 5, she could already speak several languages. By 13, she could speak so many languages that they called her the little polyglot, which means somebody who can speak a lot of languages. She could speak Greek, obviously Italian, Latin, French, German, almost all the languages. But she had an affinity for math and started studying math. And she was fortunate enough to come from a well-to-do family, so she was able to pursue her studies. She later became one of the few women professors at the University of Bologna. And one of the problems she studied was this equation that I put on the board. It later became known as the Witch of Agnesi, and the reason it was called that was not because it had anything to do with witchcraft or that Maria was a witch. It actually was a mistranslation over the years, and there's some controversy as to how it was mistranslated. About the closest I can think her graph is it does look a little like a witch's hat, maybe, but that's pushing it. Turns out it's a very interesting problem, and if you'd like to study it more, I'll consider giving extra credit for anyone that can study it. But this graph can also be generated from a circle and a line going through the circle from the origin up to this top line at y equals 1, and then dropping it down, and where it intersects the circle turns out to be how the graph is generated. It's a really interesting problem. She went on to translate, write one of the first calculus books. Just an amazing woman and an amazing mathematician, and I thought you'd want to know about her. And with Halloween coming up, the Witch of Agnesi. But that's enough for today. Hopefully you've gotten a little bit out of these examples so we can start to work some problems and look at limits and actually look at what the graphs look like on Monday.